Welcome back. This will be lecture 18 of EC253C Microprocessors and Microcontrollers. In last couple of lectures, we have discussed about the call instruction and role of stack. How stack is used to actually store the address of the next instruction immediately after the call instruction, and when the last instruction of the subroutine is executed, that is return statement is executed, this address from the stack is loaded back into the program counter and the execution from that instruction is continued. Apart from this, we can use stack. A programmer in fact can use stack for manually storing the data temporarily inside the stack. What exactly is stack? I told you last time, actually stack is a section of RAM. That means memory. And it's used by the CPU to store information temporarily. Maybe by the CPU, maybe during the call instruction, or by the programmer. We have seen how during the call instructions, how during calling of subroutines, this stack is used to store addresses. And then there are also methods through which a programmer can directly store some data onto the stack and then retrieve this data later. The two instructions which are used to store the data by the programmer on the stack and then to retrieve it are known as push and pop. Mnemonics are push and pop. Push is used for storing the data. Store the data on stack. And pop is used to retrieve back this data from stack. Retrieve back stored data from the stack. How exactly this push and pop works? The general syntax of push is something like this: PUSHRR, where this RR is any general purpose register, R0 to R31. So I can write a statement like this: push R10. So whatever will be the contents of R10, that will be stored, that will be actually copied to stack and stored there. Similarly, I can write the general syntax of pop is something like this: pop RR, where RR again is any register between R3. So after pushing R10, I can write pop R12. So what will happen? Whatever is at the top of the stack, whatever was the data that was stored latest on the stack, will actually be retrieved back and stored in R12 register. So these are the two instructions used to manually store the data onto the stack and then retrieve the same data from the stack. Now there are two questions, two important concepts that we need to discuss here. I told you that this stack, it's actually section of RAM. And if you will be remembering, we have discussed the data RAM of ATmega 328, or the data memory of ATmega 328. That's actually data memory. It's actually 2304 bytes, if you will be remembering. So we have RAM something like this. The addressing starts from 0000 up to maybe 1FFF. And you also remember that this RAM, it has got many sections. The first few locations, they are used by general purpose registers. So first 32 bytes of this RAM here, these 32 bytes, they are actually general purpose registers, what we call R0 to R31. So you should be remembering that the memory location 0000 of the data RAM is actually R0. Also memory location 1F, that is the 32nd memory location, it's R31. The first few locations in this RAM, in these 2304 bytes in case of ATmega 328, consist of these general purpose registers. And then there are input output registers. We have standard input output registers, 64 bytes for standard input output registers, which contain registers like port B, port C, DDRB, DDRC, our status register, and other special function registers. And then we also have extended input output memory. In case of ATmega 328, extended input output memory is general purpose registers were only 64 kilobytes, and extended input output memory is 160 bytes. 32 bytes, 64 bytes for standard input output, and 160 for input output byte for extended input output. And then we have SRAM. The remaining of this is known as SRAM, and that is 2304 bytes. So the first question here is, where exactly will store when I will write something? Maybe I write something like this: load immediate R17 #23H push R17. These are my two instructions. A small program, there are two instructions inside a program. So what will happen when this instruction will be executed? Number 23 in hex will be stored in R17. That means it will also be stored inside this RAM, but at a location maybe here 23H. Then the next statement will be executed, and that is push statement. The push statement, as we have discussed, it means that the data in this register R17 will be pushed onto the stack. That means the data, that's 23H, will be stored on stack. But as I have told you, stack is actually a section of RAM, so it will be stored on RAM somewhere in these 2304 bytes, 2304 bytes. Where exactly? That's the question. Where exactly? When we push some information onto the stack, it will be stored onto the stack. That means it will be stored on the RAM of the ATmega 328. Now the question is, where exactly? Maybe here, maybe here, maybe in standard input output memory, that's also possible. Maybe in extended input output memory, that's also possible. Maybe in SRAM, that's also possible. So it can be stored anywhere, but we should keep track where it will be stored. In fact, the processor should keep track where it will be stored. There should be a mechanism to keep the track where this information is stored. Where is the stack exactly inside this RAM? Naturally, it should not be here. It should not be here, because these are our general purpose registers, then there will be a conflict. It should also not be an extended or standard input output register, because these are our special function registers. Again, there will be a conflict. So it should be somewhere here, SRAM, first thing. The second thing, there always should be a register that will keep track of the stack, where stack is. Or also, when we go on storing the information onto the stack, it should keep track where we have reached, where we have stored the last information that we pushed onto the stack. For this, we have a register that's known as stack pointer. Or simply we call it SP, stack pointer. So stack pointer is, what is stack pointer? Is a register which keeps track of the stack. That means it keeps track of the stack. We have stack pointer in almost every microprocessor. We also had a stack pointer in 8085 microprocessor. So stack pointer is a register which keeps track of the stack. That means stack pointer stores the address of the stack. I think that is very easy to understand. We have to store the information somewhere, and we are storing this information in stack. Stack is a section of RAM, and we need to take care, we need to actually keep track of that information, where exactly we are storing the information, and that track is kept using a register known as stack pointer. So in fact, since stack pointer keeps the track of the information that is stored onto the stack, it will keep, that means actually it will keep track of the information stored on this RAM, because this stack can be anywhere on this RAM. By default, when we power up our microcontroller, that means when we start our microcontroller or reset our microcontroller, this stack pointer has a value 0000. That means stack pointer points here. Stack pointer has 0000. Okay. So when we write any statement, for example push R16, the contents of R16 will be stored at this address mem0000. So the contents of R16 will be stored here. But as I have told you that this memory location 0000 is also R0, is also our general purpose register R0. That means there's a conflict. So before using the stack inside a program, we need to change the starting memory location of this stack. How we do it? We do it by writing an address inside this stack pointer. By writing an address inside the stack pointer. For example, if I write this address, maybe or any address inside this SRAM. For example, if you will be remembering, the last address of extended input output memory is 01, it is 00FF. So maybe I will choose an any address here. For example, 00FF01 0100. This address, the address exactly after the stack. So what I will do, I will try to copy this address onto my stack pointer. before pushing anything on the stack. So what does that mean? When I push any information onto the stack, it won't be stored it won't be stored in the memory location 000, but now it will be stored on the memory location 0100. Let me give you an example. Before discussing the example, let me discuss a couple of more things. First thing, what's the length of the stack pointer? How long is this register? It can be 8 bits, but it can be more. But it should be wide enough to address all the memory locations of RAM. And in case of our Atmega 328, there are 2304 bytes in RAM. That means there are 2304 memory locations. So if it will be stack pointer will be only 8 bits, it can only address 2 to the raised power 8 memory location. That means 4, 8, 16, 32, 64, 256 bytes. So in case of Atmega 328, this stack pointer is actually 16 bits long. And we actually have two different 8-bit registers for this stack pointer. We have SPL, that's a separate 8-bit register, and then we have SPH, it's also a separate 8-bit register. Total 16 bits. So that now it will cater to 2 raised power 16 memory locations. That means 2 raised power 16 kilobytes. 4, 8, 16, 32, 64 kilobytes. And we have maybe maybe more than 2 kilobytes of RAM, because 2048 bytes means 2 kilobytes of RAM, and 16 and a stack pointer that is 16 bits wide will cater to 64 kilobytes of RAM. So 16 bits is enough. And by default, I told you that this stack pointer has a value of 0000. That means stack pointer high has 00, stack pointer low has 00. In binary, we can call 0000 0000. Similarly in SPL also. So if we don't change the value of this stack pointer, what will happen? When we say any push, it will be actually stored in the memory location 000. If I say like this, for example, push R10, that means if this is my RAM, the contents of R10 will be stored here. R10 contents, whatever the contents of R10, and also simultaneously this stack pointer will be incremented. It will become 0001 or decremented. In some cases it is decremented also, it grows upwards. So if it is incremented, for example, let's assume for a second it is incremented. If I write another push, for example R11, so then R11, so the contents of R11 will be stored in the next memory location. But in case it is decremented, this second statement will give an error, because initially stack pointer has 0000. When we push the first data onto the stack, that means we are writing push R10, it is being executed. That means the contents of R10 will be stored in the memory location 0000 here, and also the stack pointer will be decremented. But since we have reached the last location, it won't be decremented and there will be an error. That's one thing. Now the question is, now there is another thing here. We don't actually start with 000 for obvious reasons we have been discussing so far, that because there is a conflict between general purpose registers and the stack. So we move stack somewhere else. We move it to the SRAM area. And how we move it to the SRAM area? We actually forcibly write something in the stack pointer. That means we forcibly write something in SPL and SPH. SPH. And the best thing that's written that we should write the last address of the SRAM, because in case of Atmega 328 microcontroller, stack pointer is decremented. That means stack grows upwards. When we store the first data onto the stack, it will be stored anywhere wherever our stack pointer is pointing, maybe here. After that, stack pointer will be decremented, the next data will be stored here, and so on. It will grow upwards. So the best practice is to forcibly load the last address of the RAM onto the stack pointer. And there's an instruction inside the Atmega 328 microcontroller using which we can get the last address of the RAM. That's known as RAM end. It's a function that actually returns the last address of the RAM, because in Atmega microcontrollers the size of the RAM varies from microcontroller to microcontroller. If we are knowing the last address of the RAM, then it's not a problem. We can directly load that onto the stack SPL and SPH. But if we are not knowing, we can also know, the processor can also know the last address of the RAM using this command, RAM end. So RAM end will actually return a 4-digit hexadecimal number, because this memory, these locations, this will be a 4-digit number here. It starts from 0000 up to maybe FFFF, depending upon the microcontroller. So 4-digit number that will be having, that means 2 bytes, and these 2 bytes, the lower byte that will be stored in SPL, and the higher byte in SPH. Let me show a sample program how we do it. ORG0H, this is 0 instruction. Then the first instruction I will be writing, because in this program I know that I have to use stack. So the first instruction in every program that has to use stack, or that has to use call instructions, because call instruction also uses stack, that has to use subroutines, that's calls, or programmer is using the stack using push or pop. Stack pointer needs to be forcibly fed with some other address, so that there will not be a conflict between general purpose registers and the stack. So how we do that? First I will get the RAM end, that is the last address of the RAM, in any of the registers, in any of the general purpose registers. Maybe I will start with R16, RAM end. RAM end will give me the last address of the RAM of this microcontroller, and that will be stored inside R16. But now there's one problem. This RAM end, as I have told you before, will return a 16-bit number, will return a 4-digit hexadecimal number. That means 16-bit number, 2 bytes. But this R16, it's only 1 byte long, so data will be lost. So what we do, we write something like this. LDI R16 HIGH high. For example, we are talking, as we have been discussing Atmega 328, we are talking about Atmega 328 microcontroller, which has which has 2304 bytes of RAM starting from 0000. The last address will be 8FF for 230 byte. Okay, 8FF, or we can say 08FF. So whenever I write RAM end, whenever RAM end will be executed, that will actually return this value 08FF. Previously I was directly storing this value inside R16, but that was not possible because R16 is only 1 byte long. So what I did, I write high of RAM end, and this high of RAM end will only return the higher byte of RAM end. Whatever RAM end has returned, that is 08FF, high of RAM end will only return the higher byte of RAM end. So it will return 08. That means R16 will get a value of 08. After that, I will write another instruction to get the lower byte of the RAM end, LDI R17 low of RAM end. The lower byte of RAM end will be stored in R17. That means R17 in case of Atmega 328 will have FF after the execution of these two instructions. R16 will have 08, R17 will have FF. If we are using any other microcontroller, the contents of R16 and R17 will be different. And now we have to put these contents of R17 into stack pointer. Stack pointer is a 16-bit 2 bytes long register. R16, that is the contents of R16, that is 08. Since this is the higher byte, this will be stored in SPH, the higher byte of stack, and this will be stored in lower byte of the stack. And how we do that? We use the out instruction. Out. We have discussed out last time when we discussed the ports. Actually, out instruction is used to send data to any special function register. Stack pointer is a special function register. So whenever we have to send, we have to store data in a special function register, we use out instruction. So we use out here. Similarly, DDRB, data direction register of any register, DDRB, DDRC, they are special function registers. So we use out when we have to send data to those registers. Similarly, port B, port C, they are also special function registers. So we use out when we have to send data to those registers, and those registers are also connected to the ports, the pins of the ports. So out SPH R16 and out SPH R17. So what we effectively did, we actually moved stack from here to here, because when we turn on our microcontroller by default, or when we reset our microcontroller by default, our stack, sorry, it is SPL here. By default, stack pointer had a value 0000. That means stack was pointing here, and when we will store any information into stack, that will be stored here, actually in R0, because this is also R0. So there is a conflict. So what we did, the first thing we did, whenever we know that we have to use stack inside this program, is to shift this stack to the SRAM. We could have shifted anywhere in the SRAM, but since it grows upwards, it decrements after storing the data. We started from the last memory location, and that we did using RAM end. So now the stack pointer has a value 08FF. That means stack is pointing here. Stack pointer has a value 08FF and stack is pointing here. That's the last location of RAM. So now I will write some instructions that will actually store data onto the stack. For example, first I will write some information on some registers. I write R18, I write some information, maybe 0x23, LDI R19, 0xFA, LDI R19, R20, 0x32, any data. I'm randomly writing any data onto the registers. Now during the course of the program, maybe I have to push this data onto the stack. What I do, I will write push R18, and the contents of R18, that's number 23 in hex, will be stored onto the stack. And where is stack? Stack is at 08FF. So the contents of R18, that is 0 cross 23 in hex, will be stored at 08FF. And what will happen to the stack pointer? It will auto decrement, that will be FE, and now it will point here. And if I write another push R19, whatever are the contents of R19, that is 0 cross FA, will be stored onto the stack. And where is stack pointing? It is pointing to 08FE. That means FA, the contents of R19, will be pushed onto the stack. That means it will be stored here. So this memory location, the memory location 08FE, will get the contents 0 cross FA. Actually FA, 0 cross is just to show that this FA is in hex. And now the question is, how will the pop that's retrieving data from the stack work? One thing you should remember, that we can't retrieve any data from the stack. We can only retrieve what is at the top of the stack. So if I write pop, because in pop I am not giving any address of the stack, I am just writing pop and giving the general purpose register where it has to be stored, where the contents that have been popped will be stored. Now the question is, what will be popped out of the stack? The contents that are at the top of the stack point, that are at the top of the stack, will be popped. And in this case, FA will be popped and put into R20. That means after execution of this instruction, R20 will have contents of FA. And what will happen to the stack pointer? That will increment itself and now point to the top of the stack, that's here. If I write another pop, for example pop R21, what will happen? What is at the top of the stack? This time 0 into 23, that will be popped back to this general purpose register, in this case R21. If I have not written this R21 pop, I have written another statement, push, for example I have already used R20 here, so this should be R21, so that there won't be any error. So maybe I am writing push R20. So first I did a push and then another push, then pop. Now I am doing another push. This time my stack is pointing here. So what will happen? First the stack pointer will be incremented. Earlier I told you that first the contents are stored, then the stack pointer is incremented. Okay, I think I have to look it up first, whether the stack pointer is incremented after storing the data, or is it incremented before storing the data. In any case, let me discuss that later. If another push is executed, what will happen here? The contents of R20, that's 32, will be stored here, where FA was stored, 32. And then if I write another pop R22, whatever is at the top of the stack, in this case number 32 in hex, that will be popped to general purpose register R22. This is how push and pop work. And also this stack is used during the execution of the call instruction, during the execution of the subroutines, whenever there will be a call, and that time we had a program here last time we discussed. For example, in this program, since this program uses call instruction, so naturally our first few instructions here, they should have necessarily been those instructions which actually would have shifted the stack from memory location 0000 to the end of the RAM. We have not written those instructions, but we have to write those instructions. Assuming that we have written those instructions, what will happen when this instruction will be executed? The address of this instruction will actually be stored on top of the stack, where top of the stack is, and whenever there's a return statement, whatever is at the top of the stack, that will be transferred back to the program counter. So now there's a small issue which sometimes happens. We'll be discussing that, and that will be the last thing. For example, this is my program. Slight problem with the eraser. So I have a program where I have to use call instruction. So the first thing that's necessary is to actually push the stack somewhere else. So that's done using these instructions. Alternatively, if I have known the RAM and the last address of the RAM, that's known in case of ATmega 328, we know it is 08FF, I could have simply written that in R16 and R17 and then use these two out instructions to push that value to stack pointer high and stack pointer low registers. And these two instructions actually push the stack pointer from here to here. After that, maybe I have some other instructions inside my program. Instruction 1, instruction 2, instruction 3. After these three instructions, I have a call instruction. I have not used push or pop, so I am calling some other function, maybe a function ABC. Whenever I call this function ABC, then I have few more instructions. I am again calling this function ABC, few more instructions, and this is the end of the program. Here maybe end. So what will happen here? Whenever I call this instruction, whenever I call this subroutine, whenever this instruction is executed, the program counter that will be fed a value that is the starting address of this subroutine, and stack pointer will stack this address, the address of the next instruction will be stored on the stack. That means there will be, for example, this address was A0A, so this 0A will be stored here. In fact, this can be 4 bytes, this can be 2 bytes. The address will be 2 bytes. The address of the next instruction, that will be 2 bytes. So it can be stored here 0A, and another 2 bytes can be stored here. The stack pointer will be pointing here. So this is my ABC now, and there are few instructions, and at the last there is return. Whenever this return is executed, what will happen? These 2 bytes from the stack will be popped out and put into the program counter. Fine. Now the question is, if what I did, I used a push statement here inside the ABC, inside my subroutine, push R19, the contents of R19 will be pushed onto the top of the stack. That means here. and then there was no pop step. There was only one push inside the subroutine. And when this return instruction will be executed, what will happen? The top 2 bytes of the stack, that means now this byte and this byte, will be popped back and put into the program counter. But now there is an error, because these are not actually the address of the next instruction immediately below the call, because I have manually pushed something onto the stack, manually pushed the contents of R19 onto the stack. So there's an error. So a programmer should be very careful when using push statements inside the subroutine. In fact, there should be exactly the same number of pushes as there are number of pops. The number of pops should match the number of pushes, so that there won't be an error when the return instruction is executed and the top 2 bytes of the stack pointer are put inside the program counter. And because processor knows that processor is assuming that these 2 top bytes are actually the address of the next instruction that was exactly below the calling instruction. So a programmer should be very careful when using push and pop statements inside a subroutine. The number of push statements and the number of pop statements should be exactly equal, and if that's not equal, there will always be a problem and we will have an error. I think that's it for today's class. We will be discussing a few more concepts in the next class before moving on to the next unit. If there are any questions, we can discuss those questions in the next Zoom interaction. Thank you.